Today, we're going to spend a little bit more time describing some surfaces. Now, I realize that the first thing that I put up is a curve and not a surface, but we're going to use the ideas that we get from this curve, that's not a surface, and use them to help us describe what's going on with surfaces. So when we look at this circle, x squared plus y squared is equal to 1, we know what this looks like. We have a circle centered at the origin with a radius of 1. So this particular curve is a circle centered at the origin radius of 1. So we have a circle center at the origin with a radius of 1. One of the things that we're going to look at, I'm going to put some coordinates on this, because we started off with an equation, so we should have some coordinates. And plus, we're going to use the coordinates in our various breakdowns of this circle. So, not really surprising, we're all familiar with the equation for a circle. If not, then certainly at this point, after what I've said, you kind of have to pretend to be. So you're like, all circles, equations, what's going on here? But then I'm like, oh, remember all this stuff? And so as a student, you're going to be like, oh, yes, of course I remember all that. What we notice here is that when we draw this circle, we cannot write this as y with y as a function of x, and we can't solve for x as a function of y. So we can't write this circle as a function. We can't describe the circle with one function. So note, we can't describe the circle with a function. We can't describe this circle with a function. With a function, any input should lead to exactly one output. Oh no, that's a one-to-one function. But each input should have only one output. We can't have an input and come up with two different outputs. We can have outputs match, but we can't have an input having an or statement in it. When I plug in this x, I don't get one value. I get this value up here, and I get the value down here. When I plug in this y, I get an x value. There's two x's that correspond to that y. So we can't solve this for one of the variables. I can't write it as y is some function of x, or x as some function of y. Not with a function. Not with one function. And I picked this example because we know exactly why that is. It's those squares. Squares, even exponents in general, squares in particular, because they're the first ones we come across. But even exponents don't respect negatives. Even exponents are those friends that are always trying to cheer you up just by saying, hey, cheer up. I mean, that's just not how sadness and depression works. If it was, there wouldn't be like therapists that people have to go to and see for a long time. You just walk into the therapist's office, the therapist would just be like, oh, cheer up. And you're like, oh, thanks, doc. And then you'd walk out. That's just not how it works. But even exponents are like that. They're just like, I'll make everything positive. You know what I mean? And we know where this comes from. That's why I started with this example. If I try to solve this equation for y, I have to do a square root. And because we're trying to solve and find all the values, we need a plus or minus. So we know where this comes from. y is equal to plus or minus the square roots of 1 minus x squared. So here are our two outputs, the plus and the minus. That plus and minus part is why we can't have a function. We have two functions to build this circle, the positive square roots and the negative square roots. So we know that. Now we want to take that plus and the minus and see what it means for the circle. So we have these two functions. Y equals plus the square root of 1 minus x squared is the top half of the circle because the y's are all non-negative. So here's the plus square root of 1 minus x squared. And then the bottom half of the circle is the minus square roots of 1 minus x squared. The same thing happens if we tried to solve for x. So if we try to solve for x, we would write x is once again plus or minus the square roots of 1 minus y squared. Now in this case, we'll have two functions where x is positive and where x is negative. So instead of getting top half and bottom half where y is positive and y is negative, we'll get right half and left half where x is positive and where x is negative. So x equals plus the square roots will give us the right half of the circle where x's are positive. And then so the other part of the circle will be the place where the square root is negative. And so the left half of the circle will be minus the square root of 1 minus y squared. And if we put the plus and the minus together, then we'll have the entire circle. So y is positive is the top half, y is negative is the bottom half, x positive is the right half, x negative is the left half. We need to start looking at things like this because not everything can be described with a function. Not everything can be described where one variable is a function of the other variables. Because I know some of you, after I said, no, this is not a function, are like, oh, what about parametric equations? I'm like, oh, fine. We can't write y as a function of x or x as a function of y. We can define x and y independently as functions of t. But that's for later. So this is familiar. We know how circles work. We know why we can't write it as a function, but we wanted to make sure that we had the detail. Top half of the circle, bottom half of the circle, right half of the circle, left half of the circle. We want this so that when we push this up one level, so x squared plus y squared plus z squared equals 1, we know that we go from a circle, a one-dimensional curve in two-dimensional space, to a sphere, the surface of a sphere. So now let's upgrade to a sphere. Like we saw in our catalog of surfaces, if we take x squared plus y squared plus z squared is equal to 1, Now we're dealing with a surface in 3 dimensions. So this is going to be the outer shell of the sphere. Because here's where all these values are equal to 1. This is every point x, y, and z that is 1 unit away from the origin. That's the other thing I think I forgot to point out. When we write x squared plus y squared is equal to 1, we're just getting this circle, the outer ring, because this is the set of all the points where that are 1 unit away from the origin. So we describe that with x squared plus y squared equals 1. If I wanted to fill this in, if I wanted a solid circle and describe the area, then I would just say x squared plus y squared is less than or equal to 1. And now I'm dealing with a region, a circular region. But when we write the equation x squared plus y squared equals 1, we're just getting this curve in R2. Similarly, when we write x squared plus y squared plus z squared equals 1, we're getting a surface in R3. And we have exactly the same issue that we had in the circle situation. We can't describe this sphere where one variable is a function of the others. And we're going to do the same things. But instead of just 2 choices, we have 3 choices. I can't solve it for z, I can't solve it for y, I can't solve it for x in one function. Once again, it's because the x squared, the y squared, and the z squared are all being squared. So when we solve, we're going to introduce those square roots, which means if we want to get everything, we got to have a plus or minus. So if we set up our coordinates where z is up and down, relative to the paper and our perspective, y is left and right, and x is forward and backward, the usual way. If I solve for z in this equation, I get a plus or minus. I'll have z is equal to plus or minus the square roots of 1 minus x squared minus y squared. The plus or minus means we're not dealing with a function, because we got these 2 outputs for any input x and y, the one above the xy plane and one below the xy plane. And so the 2 functions here are the top and the bottom halves of the sphere. So we'll have the top and the bottom halves of the sphere, above the xy plane and below the xy plane. When we solve for y, we'll be looking at the right and the left halves of the sphere. So the y equals will be right and left. And then when x is equal to a function of y and z, that will be the front and the back. We should be more specific. So when I say top and bottom half of the sphere, if my problem happens to be at some funky angle and my axes aren't just the normal way we have them, We could think of the top and the bottom half as being above and below the XY plane. It's the XY plane that cuts through the middle. And so right and left, we could think this as right and left of the XZ plane. And here we can have the front and back relative to the YZ plane. Oops, not of the YZ plane. So ahead of the YZ plane and then behind the YZ plane. So if we had x squared minus y squared minus 1, if z is, that's not the same equation. So we're trying to write, the surface is an equation involving 3 variables, x, y, and z. And it's, to get a surface, you have to have 3 variables running around. Just like to get a curve, you have to have 2 variables running around. So the x squared and the y squared are both negative, and the 1 is positive. So these are the things that we want to think about when we have these x squareds and y squareds. When you start seeing things like square root of 1 minus x squared or square root of 1 minus x squared minus y squared, you want to start thinking of halves of circles or halves of spheres. And remember, the sphere is the shell of the sphere, not all the stuff inside. If I want to make my sphere solid, instead of saying x squared plus y squared plus z squared equals 1, I would have x squared plus y squared plus z squared is less than or equal to 1. And that's all the spheres that have a radius between 0 and 1. So that would be a solid sphere. So we want to make sure that we're talking about the sphere or like a solid ball. So if we write this as less than or equal to 1, this is how we describe all the points that are between 0 and 1 units away from the origin. So the distinction I want to make is when I write x squared plus y squared plus z squared equals 1, that's all the points that are 1 unit away from the origin. That's how we describe a sphere. It's everything that's the same distance from a single point. In the same way, if we drop it down 1, when we write a circle, x squared plus y squared equals 1, a circle is all the of radius 1 is all the points that are 1 unit away from the center. And the way to describe that is with this equation, x squared plus y squared equals 1. It's a variation on the distance formula. Or maybe the distance formula comes from this description. At this point, we're going in circles, which is actually appropriate. So this is just the points that are 1 unit away from the origin. when we write this equation. So this point does not satisfy the equation because it's only a half a unit away from the origin. So the circle is just the ring around the outside. If I want this region, if I want to describe a circular region, and I want to describe everything that's between 0 and 1 units away from the origin, then I could say less than or equal to, and that fills the circle in. So if I say x squared plus y squared is less than or equal to 1, that's going to be a circular region where we have a whole area. And then the same thing happens when we're dealing with a sphere. X squared plus y squared plus z squared is equal to 1 is just that spherical shell, just the outside. If I want to describe a solid with everything inside as well, then I can use an inequality and say less than or equal to 1. And what we're doing when we put this less than or equal to is that x squared plus y squared plus z squared is equal to 1, then also less than or equal to a half, less than or equal to a quarter, less than or equal to all the real numbers between 0 and 1. Because we know it stops making sense, at least for real values of x squared, x, y, and z. It stops making sense when the radius drops down to 0. Any questions? So this less than or equal to, that's how we would make the sphere a solid sphere. We want to make sure that we're just talking about the onion, the orange peel, not the orange inside. I like an onion. This is we're just describing the onion skin on the outside that you take off before you get to all the stuff inside. So what you want when you're peeling an onion is not all the stuff where it's equal to 1. That's like that weird papery stuff on the outside. The onion that you use in the cooking is x squared plus y squared plus z squared is strictly less than 1. That means you're not including that outer onion skin. You just want the stuff less than, strictly less than. Just like when you eat an orange, you don't want less than or equal to 1, because that would include the peel. You take the peel off and you look at where x squared plus y squared plus z squared is strictly less than 1. Or strictly less than the square of the thickness of the onion peel, I suppose I should say to be. Because I'm just worried I'm going to get well actually'd. True, peels are sometimes a good thing to use. I mean, if you're mixing an old fashioned, you're going to need the orange peel. I've got a lemon tree out back, and sometimes you just need the peel parts. You need the lemon zest. Questions? Yeah, I should have stuck with the onion one, because I can't think of anything where you actually use that papery onion part. Not that I have a lot of experience cooking around the world, but I'd be surprised if I started peeling an onion and someone's like, oh, no, 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 save that part. It could be the purple ones. You could use it as a dye. I wasn't thinking of a purple onion. I was thinking of like a white onion. So I don't know, if you could use the white onion to dye stuff, then I'm just even more wrong. All right, any questions? Oh, see, that's the thing. I can't have a hamster. I have a cat. And one day we would just end up finding an empty hamster cage and then the cat just looking at us like, oh, I don't know, he must have gotten out. I guess he just wanted to escape. No, no thanks, I'm not hungry. Let's talk about what happens if a variable is missing. And we're going to start with the same circle that we had before. So we're going to consider x squared plus y squared equals 1, but now we're going to consider this in R3. So in this sense, since we're looking at this in R3, I'm using the word missing, like the z is missing. If we have an equation relating x and y and z is not appearing in the equation, but I still want to put this equation in R3. So I'm thinking of z is missing from the equation. It describes sports cars. Although Nissan is bringing the Z back. So Z is missing from the equation. I know there was like the whole 370Z, but let's face it, Nissan really left that car behind. It hasn't really changed since they first bought back the 350Z. So pour one out for the Z car. I hope the new Z gets some respect from Nissan moving forward, not just like make a car and then dump it. You know what I mean? All right, so let's think about this equation, x squared plus y squared equals 1. Think about this, x squared plus y squared equals 1, but as a function of 3 variables. So we know what we're looking at from the top-down view. I almost drew the x and y axis first. When you're drawing circles and you're going to put a grid on them, you draw the x and y. You draw the circle first. So here's our circle, x squared plus y squared equals 1. But what we want to do is consider what this is going to look like if there's also a z. And the answer is, it just always looks like this. This equation only cares about the relationship between x and y. It looks the same for all values of z. So since z is not in the equation, the graph looks the same for all values of z. Since z is missing from the equation, so the graph looks the same for all values of z. So top down, we always see the same thing. So if we put this in 3D, it'll just look like a cylinder or a tube, just a cylindrical shell. So if we have, we put our x and y axis in our usual spots. in the XY plane, this is the circle that we're looking at. And if we now put the z-axis on here, we're just going to get this same picture for all the different values of z. So if I pull a z-axis going straight up here, then we're just going to take this circle and pull it up into this cylindrical tube. And then it'll keep going down as well. So if one of the variables is missing, then the graph always looks the same. You can just look at the plane involving the two variables that are left, and we'll just always have that same graph. So it looks the same for all different values of z. This equation doesn't care about z. It's just going to look the same for all the different values of z. This is in fact something that we have covered in the past. Maybe not y'all and myself, but this is something that we already do. So imagine a constant function of one variable. So C also, constant function. If I have the equation x equals 2, I can consider x equals 2 as an equation in R2. So in this sense, I'm saying that y is missing from the equation. Well, in R2, we know what x equals 2 looks like. In R1, well, I guess we know what it looks like in R2 as well. If we just have R1, we just plot the point x equals 2. It's just that point. But in R2, we don't care about what y is. So long as x is equal to 2, this equation is happy. So it looks the same for all values of y. And so we get this vertical line. So x equals 2 for all the different values of y. And we can take this a step further. We can look at the equation x equals 2 in R3, where x is equal to 2, not only for all values of y, but for all values of z. So all pairs y and z. So what are we going to get if we graph x equals 2 in R3? Take a moment and think about x equals 2 in R3. we'll end up with a plane, because we'll just take this plane, this vertical line in the XY plane, and say it's going to look like this for all values of Z. So I'm just going to take this line and project it up into the Z. For all values of Z, this is what we'll be looking at. So I'm very unwisely going to try to draw it. Because at least planes, you can put axes on first. So we started off with x equals 2. And we did this for all values of y. So there's that vertical line that we're looking down on, not like in a condescending way, just like from a physical position way, looking down on this line. And this line is going to be what we use for all values of Z as well. So I'm just going to take this and extend it up and down into a plane. So I'll have this plane perpendicular to the YZ plane. And this is the plane where x is equal to 2. Note that the YZ plane is just described with the equation x equals 0, because that's what everything looks like on the YZ plane. That's where x is equal to 0. The XY plane is where z is equal to 0. I can't remember which one I left off. The XZ plane is where y is equal to 0. So x equals 2 just takes that YZ plane and moves it over 2 units to where x is equal to 2. Any questions? How's everybody okay? Just like circles and spheres and planes and lines. So when things get more complicated, these are the kinds of things that we want to fall back to. We want to think about how we create higher dimensional things from lower dimensional things. The idea of, like, for example, taking this circle and just stretching it for all values of Z, this is something that we do anyway. We already know how to do this process. So it's how we build higher dimensional things. We could start with a point. So a point is 0 dimensional. But if I take that point and I extend it through, let's say I'll just move this point to the left, start with a 0 dimensional point. If I slide this to the left, that's the right. If I slide this to the right, I can create a 1-dimensional segment. Just by taking the point and projecting it through a dimension that I wasn't already using. I can take my 1-dimensional segment and project it into a 2-dimensional square. Just by taking this segment and projecting it through one of the dimensions that I'm not already using. So I push this up. Say vertically, because I haven't used that dimension. I just get this copy of this segment in a different dimension. And all this came from a point, as this point got pushed out to this corner here to make a segment. And I took this segment and pushed it up through a dimension that I wasn't already using. So you can probably guess what's coming next. I want to take my 2-dimensional square and push it into a dimension that I'm not already using. And that's going to make a cube. My limitation here is that I've only got 2 dimensions to draw things on. I suppose I could get like one of those 3D pens and like write up this way, but. So I'm going to make a 3-dimensional cube. And we do that by pushing this square into a dimension that we're not already using, although my 3 is a little squashed. So I push my cube into a dimension that or my square into a dimension that we're not already using. Where here's our original point, here's our line segment. Here's where the line segment got pushed when we made it 2-dimensional. And here's where we turned it into a square. And so we end up with this cube. We take the point, we stretch it into a segment. We take the segment and stretch it into a square. And we take the square and project it into a cube. Any questions? So there's nothing that's going to stop us from keeping this process going. I just took, this all comes from this original point. I put this point, and then these 2 points got projected into these corners. Then I just took those 4 corners and projected them into a dimension that I'm not already using. Even though this is all on the same paper, I just had to project each of those that 1 point into 2 points, those 2 points into 4 points, those 4 points into 8 points. So the only thing stopping us from continuing is how do we imagine what's going on in 4 dimensions? We don't have, maybe we don't have, maybe you do. Maybe you have a picture in your mind of what a 4-dimensional cube looks like. But it's not as helpful if you can't describe it to the rest of us. So even if you're like, oh, I can see what it looks like. Everybody else is like, oh, great, describe it to us. And you're like, oh, I can't, you just have to understand. If it's just something that we have to understand, you might as well just be making things up. You might as well just be pretending. So all we need to do to make a 4-dimensional cube or a 4-dimensional hypercube is take this cube and project it into drag it into a dimension that we aren't already using. So I just need to take these 8 vertices and drag them to a dimension that I'm not already using. And then we can make a 4D cube. I would look that up because I can't remember. I think it's called a hypercube. So the problem is, if I try to draw this, it's going to look a mess because I've already squashed one dimension out of this object. Now, if I try to draw it on a plane, I'm going to be squashing 2 dimensions out of it. But all we have to do is project each of these points into a dimension that we're not already using. I know it looks crazy that I'm just connecting these wires, but I mean, where is that dimension going to be? And then this line segment will be up in here. This line segment will be projected out to here. These 2 line segments will be projected out to here and here. So as a thought exercise, sure, no problem. I'm just like connecting a bunch of dots. But helpful? I don't think it's not helpful to me. I love doing this little exercise just to make sure if I can keep track of things. Oh, great, I'll put these vertically. There we go. But that always happens where I have to draw one. It's like all curvy and. Yeah, I should pay attention to the MCU. No, not gonna write that. Now, if I wanted a 5-dimensional thing, I would just take each of these, all of these corners and project them out into a dimension that I'm not always using, not already using. I could draw that on this piece of paper, but it would just be like a jumble of lines. Any questions? How we would want to view this 4-dimensional thing is by looking at level solids. Look at all the different solids that make up this one. Any questions? All right. If you're worried about drawing something like this, that's going to be the final exam. No, I'm just kidding. Final exam, problem number 1. Make Leach picture a 4-dimensional object. That's why no one ever passes my class. I'm just kidding. I just happen to like this exercise where we take points and just stretch them out. Imagine starting off with a 0-dimensional point, stretching it into a segment by pulling it into a dimension that you're not already using. Make a square by pulling into a dimension that you're not already using. Make a cube by pulling into a dimension that you're not already using. Keep going. Take that cube, pull it into a dimension that you're not already using. All right. Your current project is to finish up the homework from chapter 12. You'll notice that I haven't talked a lot about chapter 12, section 6. Chapter 12, section 6, that's where a lot of the rigorous stuff happens, where we start making things fit the definition of limits and the definition of continuity. I think a more important project for us to work on is to practice picturing surfaces and matching surfaces and equations, so that because equations are how we're primarily going to be interacting with surfaces, especially when the surfaces jump past 3 dimensions. I have to start picturing things in 4 dimensions. My dog has decided it's time to play. So, hey, bud. Dude, I'm recording a lecture right now. He doesn't care. He wants to play red thing. I know, I see it. So your priority should be the first 5 sections. Work on section 6. Once everybody has had a chance to work on those problems and get stuck on them, then we can figure out where we're stuck. If all you've done is just read the problem once, you're not stuck yet. You haven't suffered enough. I mean, you haven't struggled enough. Late homework is always okay. I'd rather have work done late than just not done at all. If I start penalizing late homework, then people are just not going to do it. You know what I mean? Now, it is not okay, since late homework is okay, it is not okay to put chapter 12 homework off until December. And it's like, all right, I've got 2 weeks, so I guess I better get started. You're going to have like 50 assignments to do in the 2 weeks, and the results are not going to be good. You know what I mean? All right. So that's going to do it for today. My dog is pouting now because I stopped playing with him. Definitely pouting. So that's going to do it for today. That's going to do it for this week. We don't have any meeting tomorrow. So, and we don't have a meeting on Monday because I think Monday is Labor Day, isn't it? No, not yet. I thought it was a week later than it was. So I will see you all on Monday. If you have questions on problems, then send me an email and we can either answer questions over email, or we can set up a Zoom during office hours tomorrow. My office hours tomorrow nominally from 9 to 11, but I can meet later because I know some of you have classes from 9 to 11. All right, that's going to do it for today. That's going to do it for this week. I'll see y'all on Monday, and thanks for playing.